My name is Berger. This is my submission for Lab 1, Constant Velocity Motion, and the course, Physics 2211, with Dr. Berger. The purpose of this lab is to compare the observed position of an object at constant velocity to a program-generated model of the object's predicted position. In order to do so, a video recording of a ping pong ball rolling across the desk was uploaded to the software program Tracker. Tracker was used to accurately record the ping pong ball's observed position, as shown here. To gather the predicted motion of the ball, a Python program was created via GlowScript, as shown here. Finally, the observed position and predicted motion were plotted via Google Sheets and compared, as shown here, in the next slide, and here. The fundamental physics principles involved in these models includes Newton's first law and Newton's second law. Newton's first law states that an object in motion will stay in motion unless acted upon by another force. This is supplemented by Newton's second law, which states that the force acting upon an object is the product of mass and acceleration, or F net equals ma. Given that the ping pong ball is in constant velocity, there should be no forces acting upon the ball in this motion path. Taking into account Newton's second law, without any force, there should be no acceleration. Without acceleration, the velocity of the ball should be constant. Knowing these two fundamental principles, the object's position can be predicted via the program and GlowScript. But before we start coding, we need to make some calculations. Keep in mind that this data was gathered from the Tracker software program. Here we can see the observed start time at 0 seconds and the ball's initial position in the x direction. Using this point, along with the next consecutive point, we can calculate the ball's initial velocity as the average between these 2 points. Even though this is an average velocity, given that the time interval is very small, this would do well enough for initial velocity of our ball, and this calculation can be shown here. Finally, we can take the time of lapse observation, which happens to be 1.285 seconds. Now that we know this information, we can code the predicted position of our ball. First, we can set the ball's mass to 2.7 grams, or 0.0027 kilograms in standard SI notation. We could set the ball's initial position to the vector we showed earlier, and the ball's initial velocity to the vector we calculated earlier. We could set t, the time, to 0, and the change in time, 1/100th of a second. Before we get into this loop, we must realize that the ball is in constant velocity. Therefore, there is no acceleration, and thus no net force acting on the ball, which is why the F net vector is set to 0, 0, 0. To explain this code, each iteration of this loop updates the ball's velocity vector as well as the ball's position vector until the time reaches 1.285 seconds. When we run this program, it will give us a graph and data analysis of the predicted motion of the ball, as we can see here. Now, as opposed to the predicted position of the ping pong ball, the object's recorded position was determined experimentally through recording and using the Tracker software. The Tracker software essentially allows us to do a frame-by-frame analysis of the motion of the ping pong ball. In the bottom left, we can see the frame number of the ball. And as we play the video, the frame number updates, and so does the position vector of the ping pong ball. As the frames of the videos progress, so does the position of the ping pong ball. Each diamond represents the new position of the ping pong ball after one frame. And here, all those diamond positions are recorded in the table and are also graphed right here. Now that experimental and computational data have been collected, they can be compared via Google Sheets by placing each respective data group in its own column, as shown here. Taking a look at the data, there's a discrepancy between the experimental data in blue and the model data in red. In order to explain this discrepancy, the experiment systems and surroundings must be detailed first. The system is the ping pong ball, and the surroundings are the desk and earth. Additionally, the initial conditions of the experiment involve the ball starting from a resting position, then accelerating to its maximum velocity, then rolling in constant velocity. However, there is a fundamental physics error present in this lab, which is the negligence of air resistance, which is a force that acts in the direction opposite of motion, similar to friction. The presence of air resistance supports the discrepancy between the experimental data and computation media, where the air resistance acts as a force that slows down the ping pong ball. This is shown as the slope of the experimental data is slightly slower than the slope of the model data, which signifies that the velocity is slightly slower or decreases over time. Now, what would happen if the axes were flipped? If the y-axis were flipped, the position, then the object would be moving in the opposite direction. So instead of going from the bottom left to the top right, it would go from the top left here to the bottom right in quadrant 4, somewhere down here. However, if the x-axis were flipped, then the graph would move up into quadrant 2, so quadrant 1, where instead of moving bottom left to top right, it would move from bottom right to top left. The right was defined as the positive direction of this experiment, which is why the graph moves in the positive y and the positive x direction. That wraps up Lab 1, Physics 2211.